Welcome everybody to the Cloud Online Meetup. Today's topic is going to be MidoNet, which gives OpenStack Neutron a boost. And the speaker is going to be Cynthia Thomas from MidoCura. So MidoCura's MidoNet is a virtualization overlay that is completely open source, providing a distributed architecture that solves the shortcomings around OpenStack Neutron network plugins. And in this meetup, we will discuss the importance of distributed architectures for OpenStack networking and critical considerations when selecting a network provider and installation guidelines for a basic proof of concept and production deployments based on actual customer use cases. A few logistics before we get started. This session is going to be recorded, so just in case that you want to share it with colleagues, you will be able to do so in hopefully the next 24 hours. The slides will be available as well. And in case you have any questions, feel free to ask those using the chat window on the left-hand side of the web panel. And with that, let me hand over to Cynthia. Cynthia, the stage is yours.
Great. Thanks, Raphael, and thanks everyone for joining today from around the world, I'm sure at various times. My name is Cynthia Thomas. I'm a systems engineer at MidoCura. And I'm going to talk to you about our product called MidoNet, which is actually an open source product, and how it gives OpenStack Neutron a boost. And as Raphael outlined, we'll go through some of the architectural benefits, some comparisons, and what you should keep in mind when considering an OpenStack Neutron plugin. Here's just briefly the agenda for today. I'll talk a little bit about MidoCura, give you an introduction to give you guys some awareness of who we are. I'll go over the product called MidoNet, its architecture and comparisons. That being said, I'll mention some things that are important to consider during a proof of concept and during installation. And then I'll go through the MidoNet packet walkthrough, so that you understand how a packet flows through an OpenStack plus MidoNet environment from end to end. Finally, I'll go through some use cases, some things that are particularly important to our customers and potential customers out there when considering an OpenStack Neutron plugin. So about our company, we were founded in 2010. We are a global company distributed across main sites in Tokyo, San Francisco, and Barcelona. Some of our initial founders, basically our CEO and our chief architect, are actually were Cornell graduates and studied under Werner Vogel, the CTO of Amazon. So some of the most important things to them are building systems in a distributed and highly scalable manner. We've been a significant contributor to OpenStack networking, specifically Neutron, since the B release, and we've been an early member of Open Daylight as well. So that being said, we have a large ecosystem that continues to grow through our customers globally, our partners worldwide, being resellers or complementary solution providers, as well as resellers outlined here. So I thought I'd briefly go over just the evolution of network virtualization and talk about the innovation in networking agility. So initially, as we know, when workloads started to become more and more virtualized, the initial network reacted more in a way using protocols that already existed. For example, using the VLAN approach. And VLANs allowed large layer 2 subnets to exist such that things like live migration could be performed so that a VM could maintain its IP address while being migrated. But for those who are familiar with VLANs, they can be really difficult to maintain and be unstable, as a majority of the time the considerations in loop collisions are handled by spanning tree. And spanning tree has large reconvergence times, for example. And in the end, this was a very manual and complex way and more reactive way to a problem of increasing virtualized workloads. Then next came the OpenFlow approach, which is also a more reactive approach. Those familiar with OpenFlow, it's a communication-based protocol where a controller pushes down some rules based on this OpenFlow protocol to hardware and implements these flow changes in hardware. So that being said, it's still limited to the scalability of the hardware memory, and it's also hard to manage and impacts performance greatly, and still requires a tenant state in the actual physical network. Finally, a more proactive approach is the virtualized network overlay approach. So in this approach, we use things like VXLAN or GRE, which were VXLAN, for example, was basically created to solve these problems in the virtualized workload environment, such that we can initiate these overflows or overlays right from the server, right from the edge, and carry the flows over the underlay network. So you can maintain, for example, a layer 3 class network underneath, which is very strong and resilient to changes that might happen in the overlay, and allow that cloud agility to happen just through changes in the VXLAN headers, for example, that would be controlled at the edge. So in turn, the network virtualization overlay approach is a more cloud-ready approach and allows for unlimited scalability, and we'll see why that is when we get further into distributed architectures. And also, these are based on open standards, so it's a very open approach as well. And in turn, you're not limited or forced into any kind of physical change on your underlay, so no physical changes on the network, which allows changes and improvements to be made in software and allow improvements just to be delivered more quickly that way. So those familiar with OpenStack, previously, up until now, the default plugin was the OVS plugin. So now I'll go over the OVS plugin and talk about some of the functionality and limitations behind the previous architecture. Also to mention, when it comes to a proof of concept, you can lay out this OVS default plugin in a non-HA manner, and it's fine, but as soon as you go into an HA mode, there's complications and scale issues, and we'll see why that is right here. So basically, this diagram depicts basically the default OVS plugin architecture, and for those who are familiar, there's a single point of failure through the Neutron network node. So some of the components of the OVS plugin are the OVS agent, the DHCP agent, the L3 agent, and the IP tables component. So as you can see here, the L3 agent resides on the Neutron network node as well as the DHCP agent. And the compute node contains the OVS agent. So the OVS agent residing on the compute nodes receives tunnel flow setup information from the OVS plugin and programs the Open vSwitch to set up tunnels and send traffic through these overlays. So in this example here, we're showing GREs, but it could be VXLAN also. The DHCP agent residing at the Neutron network node sets up the DNS mask in a namespace per subnet created by the tenants, for example. And then finally, the L3 agent portion of the OVS plugin orchestrates the changes for IP tables or any kind of routing decisions, or even especially important NAT tables for translating network addresses typically for north-southbound traffic. So talking about the challenges with this previous OVS plugin, the Neutron network node, as I mentioned, is a single point of failure in this architecture. So by default, it's a single point of failure, and something additional needs to be done in order to create an HA environment. For example, using CoroSync or some kind of heartbeat protocol or script. And that, of course, can take into account failover time to behave in an active standby mode. Also, obviously, this is a challenge of scale. As compute nodes continue to scale out, there's still that single Neutron network node in the network. So forcing the traffic to get routing decisions from any kind of tenant or inter-tenant traffic or just north-southbound traffic, the location and the compute power of this Neutron server becomes extremely important and can quickly become a bottleneck and hotspot in the network. Also, as you'll see in the coming slides, there's other ways to approach these network functions. So we consider this OVS plugin to be inefficient networking, since you need to go to the Neutron network node in order to get any kind of IP tables functionality, routing decisions, or even NAT functionality. We consider this to be inefficient networking, since you're basically relying on this Neutron network node, kind of like a network appliance within the network, to make these kind of routing decisions or network appliance type decisions. So now I'll talk about Midokura's product called MidoNet. And also, as I mentioned, this is an open source product available for download at www.midonet.org. So MidoNet is a network virtualization overlay platform. So everything is done completely in software. We're as agnostic as possible to the underlying infrastructure. That being said, we require IP connectivity between our components. And we get a plethora of features listed here. For example, logical layer 2 switching. So since we leverage VXLAN or GRE tunneling, we can go beyond the scale of VLAN IDs to provide logical layer 2 networks across an OpenStack plus MidoNet environment. We also have logical layer 3 routing, which allows tenants to have isolated networks with overlapping IPs, and also translate and forward traffic across many subnets through our logical layer 3 routing. We also provide stateful and stateless NAT, and this is also done in a completely distributed manner. We also provide distributed firewalls, so the equivalent of ACLs, or from the OpenStack world, security groups, and we do this in a completely distributed manner. Additionally, another one of our differentiators is our logical layer 4 load balancing. So we allow tenants to create load balancers for their networks and point to pools of back-end servers, or VMs in the case of tenants. And this is also done in a completely distributed manner. So all of these things are achieved with rather VXLAN or GRE tunneling. Obviously, there's some advantages to VXLAN when integrating with some top-of-rack vendors who support the OVSDB protocol, for example, like Cumulus and Dell. Also, VXLAN offloading on some NIC cards is also a benefit to using VXLAN tunneling. Finally, we provide everything with our MidoNet API, which basically aligns with Neutron API. And with our API, we also have a CLI and a GUI for the availability of the user, but which could also be scripted against for configuration purposes. Next, I'll talk about our distributed architecture and its components. So this diagram depicts our architecture where at the top we have our network state database, which is a completely logical or passive database storing our logical topologies. Towards the center, we have what represents compute hosts in the OpenStack environment. And this is where our agent resides, at the edge on the host. Finally, towards the bottom, we have our gateway nodes. And we also have a scalable gateway that acts in an active-active manner. In this case, we also support BGP to allow for a dynamic routing protocol to dynamically update the routing table for usability of routes in and out of the OpenStack environment. As I mentioned earlier, we're completely done in software, and we implement a network virtualization overlay. Towards the center, we have basically the underlay or the physical network. We recommended layer 3 cloths here, but it's up to the administrator to decide on what they'd like to use underneath. And they can use existing infrastructure today as long as all of these components have IP reachability. So just to give you an overview of how the logical topology maps to the physical world, at the top, as you can see, there's some concepts that would be familiar to you in OpenStack. So for example, this turquoise router and switch could represent a particular tenant in OpenStack. And same with this purple network up here. We actually have a new construct called the provider virtual router. From an orchestrator or even a tenant's perspective, this is completely done in the background from any kind of configurations in OpenStack Horizon. From a tenant's perspective, the purpose of the provider virtual router is basically an egress point to the external world, external networks or the internet. But basically their tenant router connects to the MidoNet provider router. And from an OpenStack administrator's perspective, this provider router is a logical concept that can scale across all the gateways that I mentioned that are here listed below in order to connect up to your upstream routers with BGP. So basically, as you can see on the right-hand side, for a tenant's network, the virtual ports map to that of VMs on the compute hosts. And the compute hosts also have our MidoNet agent residing on them. Also in the underlay, you'll see that the MidoNet agent also resides on our gateway nodes, the lower left-hand side, where BGP is running, and BGP sessions can be set up with upstream routers to allow for a dynamic routing protocol to update the routing table for external networks. Also in the middle here is our network state database, and that is a completely passive database. It's actually Zookeeper and Cassandra, and it's not modified in any way, and it basically contains the logical topologies and does not contain our agent, but all of these components are IP reachable on the underlay, the private IP network. And that can be an environment that's existing today. You can leverage your existing network today. So that being said, as you can see here, we strive to have a highly available and scalable architecture without any single points of failure. So we encourage deploying our nodes in a highly available manner, with at least 2 for failover. And they'll always be all active, so there actually is no failover time. And also, the network state database we encourage to be deployed in quorum, such that we encourage you to just deploy at the minimum of 3, depending on the size of the network. And then, as we'll see, the MidoNet agents on the compute host actually have all the intelligence they need in order to apply the network services to the VM's traffic flow. So as you can see, there's no single points of failure, and we have the ability to scale out highly. So just a reminder, the challenges we spoke about with the OVS plugin was that there was this Neutron network node as a single point of failure. Challenges at scale, since we're pointing traffic towards that network node, and it quickly becomes a hotspot within the network. And also inefficient networking, since layer 3 routing and IP tables functionality and NAT functionality, for example, have to be decided on the Neutron network node. With MidoNet, we have a completely distributed edge model. So as I mentioned, the software that's residing on the compute host has the intelligence to make all the security group decisions, all the routing decisions, even layer 4 load balancing, floating IP, and that basically. All is done at the compute edge. So in comparison to some of the other plugins out there, they have what could be called a centralized controller model. So there might be an SDN controller within the network that's handling processing of flows. So we see this as a weakness because this SDN controller has to be invested in and decided upon in order to meet the needs of the growing network. So rather, it's a large investment up front for processing power that could go underutilized, or it could quickly become exceeded by the demands of the network. In the MidoNet distributed model, all the intelligence is completely distributed, and processing power happens at the compute edge. So as your network grows, your compute power grows, and thus your network decisions that can be made at the edge allows your network to grow. Also, when considering Neutron network plugins, there are those who have the active standby gateway model. So the gateway being your ingress point in and out, or egress point in and out of the OpenStack environment towards the internet or other networks, other external networks. So as you can imagine, with the active standby gateway model, we see all traffic flows headed towards the active gateway node. As you can see from this diagram, it looks like basically a major hotspot within the network, and also have underutilized links towards the standby gateway. So you're underutilizing links and forming hotspots within the network. With the MidoNet model, we have a fully distributed gateway model. So as I mentioned, you can just keep scaling out the gateways, running BGP on each, and all of them will be active and used in an ECMP manner as long as they're IP reachable on the underlay and connects to an uplink router running BGP to maintain BGP sessions. So you can keep scaling out and increase the throughput for the egress points to external networks or the internet just by adding more of these gateways. which, by the way, is just x86 servers running our agent. So a testament to being agnostic to the underlay, and also the ability to scale out in a cost-efficient manner. So now I'll go through a packet walkthrough and just to show you how MidoNet works and how these components talk to each other. So as we all know, with OpenStack, cloud networking can be complicated. We're familiar with our customers doing proof of concepts and quickly, seeing the Neutron network node as a single point of failure is not attractive to them at all. And everyone wants a highly available network, as well as the ability to scale out. So this will show you how to build out a proof of concept. Basically, what you need is some compute hosts to dedicate to network state databases, like here in the upper left-hand side. On the upper right-hand side, we have our gateway nodes, which I mentioned can be just x86 boxes with our agent on it. Of course, we encourage a minimum of 2 to have a highly available gateway. And then install the MidoNet agent on the hypervisor nodes, as you can see below. So rolling back into the OpenStack environment, we can build a virtual network and see what MidoNet is doing on the underlay. So as I mentioned, we have that provider router to connect to external networks or the internet. So this is automatically created when a tenant sets the gateway for their router to an external network. So each tenant gets its own virtual tenant router. So as we know, we can create this through OpenStack Horizon. Each tenant has the ability to create whatever rules they'd like. So they might apply a floating IP rule, even though that's not necessary. We can handle both cases. They pick a subnet for their networks, and they can define their security group rules to allow or deny certain traffic ports. So they'll attach their tenant network to the tenant router. Now we'll spin up 2 VMs on this single tenant after the network's been set up. So as I mentioned earlier, all these constructs from OpenStack and additionally the provider router are completely logical constructs. So they're all done in software, just more for perspective on how to reach the external network or how VMs can connect to each other within the same tenant. These logical topologies are stored in the network state database. As I mentioned earlier, these are Zookeeper and Cassandra. So let's see what happens when we send traffic between 2 VMs. The first outbound packet comes from the VM and is intercepted by the MidoNet agent on the hypervisor. So this happens only at the very first single packet coming from the VM. 99.99999% of the time, the information will be stored locally already from previous initial traffic flows. So in the case where it was the first outbound packet, this packet does a query. Basically, the MidoNet agent intercepts a netlink message asking for the information for that traffic flow. And the MidoNet agent, if it doesn't have it cached locally already, given it's the first packet flow, it will query the network state database to find out the virtual topology relevant for that VM traffic flow. So The agent will pull down that information locally to the compute edge, and then it will simulate the packet going through the network and applying any necessary rules that were created by the tenant. And finally, simulating it going to the destination VM. Once that packet simulation is done, the MidoNet can create a GRE or a VXLAN tunnel to the destination compute host, where the destination agent will deliver it to the destination VM. So all the compute power, all the routing decisions, in this case there was no NAT involved, but any kind of security group rules that may have needed to be applied were done by the ingress host through this packet simulation. So that was just for the first packet of that packet flow. All subsequent packets between these VMs can fly at near line rate, given we already know the rules that we need to apply to these packets by the simulation being done. So that was between two VMs on the same tenant. A similar process is done when sending to the external network or the internet. So in this case, the first outbound packet from the VM is intercepted by the MidoNet agent. Again, since it's only the very first packet, the MidoNet agent queries the network state database for that virtual topology for the traffic flow to the external network. This time, the floating IP rule may be applied since it's an outgoing outbound packet, and the MidoNet agent applies that simulation all locally at the compute edge host. So it'll simulate the packet going through the virtual topology towards the external network. Again, any rules that need to be applied, like security group rules indicated by the tenant, or the floating IP mapping, would be done by that ingress host. Then the MidoNet agent creates a tunnel to the gateway node and sends it on its way. Since that was only the first packet that needed to have the logical pull down, the remaining can fly at near line rate towards the gateway. A similar process happens when packets are coming from the internet into the OpenStack MidoNet environment. Some things to highlight here are some of the rules that we talked about, like load balancing, for example, or security group rules applied at the edge, allow us to protect our network from rogue traffic or just achieve distributed networking. So on the inbound packet, this time the MidoNet agent, which is identical on the gateway node, queries network state database for the virtual topology. Then the agent on the gateway node will perform the simulation of the packet flowing through the logical topology from the external network to the destination host. So the simulation is done by the gateway node, and then a tunnel is created to the destination host, and the remaining packets can flow at near line rate. So again, as you can imagine, if you have inbound traffic that you need to protect your network against, let's say by only allowing certain IPs or certain port numbers to come in, you can protect your network from unnecessary traffic by blocking it right at the gateway. Also, providing like web services, you can leverage the distributed layer 4 load balancer and point to several back-end servers right from the gateway node. Next, I'll talk about some of the use cases that are relevant to our customers and potential customers. So initially, when customers hear about us or come to us, they've tried out the OVS Neutron plugin, and they see the Neutron network node as a single point of failure. And this is fine in a testing environment, but in a real proof of concept that's made to mimic something that would be deployed in production, this is not acceptable. So initially they come and they're interested in just using MidoNet as an OVS plugin replacement. But there are basically other benefits to using MidoNet in order to move towards a self-service environment. So as I mentioned a few things, we have this single virtual hop networking, for example. As I mentioned, the OVS plugin we consider to be inefficient for networking. We're applying all our layer 2 through 4 services right at the ingress host, right at the edge or compute host. So this is done in a single virtual hop. Also, we have tie-ins with our hardware vendors, such as Dell and Cumulus, to provide VXLAN hardware gateways. So this allows the bridging of virtual machines and workloads to physical servers, hanging off right off the top of rack. Also, we get great performance with our 40 gig NIC support. And another differentiator for us is also that logical layer, the layer 3 gateway node being able to be scaled out and allow for multiple BGP peers on the uplinks to have multiple egress points from the OpenStack network environment, and done in a dynamic manner. Also, as you can see here in gray, we have on our roadmap IPv6 and metering things coming in the future to meet the demands of our customers. Talking a little bit further about one of our features is the VTEP. So as I mentioned, we have some tie-ins with Cumulus and Dell, for example, of the VXLAN gateway on the top of rack. So here, basically, our network state database acts as an OVSDB client talking to the top of rack switch, which is running an OVSDB server, and exchanging MACs to do a VXLAN to VLAN mapping, or a VNI to VLAN mapping, for example. So this allows our agents to directly create VXLAN tunnels to the top of rack and map to a VLAN in order for VMs residing on the compute edge to talk to physical servers or applications that can't be virtualized. So that was it for our introduction to our product today. We encourage you to check our blog on blog.midokura.com and follow us on Twitter, and also check out our open source page, www.midonet.org.
Thank you so much. Thank you so much, Cynthia. While you were presenting, a few questions popped in, so let me walk through those. The first question is, Neutron is HA ready in Juno, so I guess it says no longer a single point of failure.
Oh, so some things about things that came in Juno. Yeah, I know that, for example, like the layer 3 agent has been pushed to the edge. If you take a look at the Juno blueprint, it's still a very complex a complex system. And there are still things that are centralized. For example, source netting is still done at a central point in the network. So there's definitely some things that have not been fully matured in that OVS default plugin as they continue to grow.
All right, the next question is, hold on a sec. Are both MidoNet firewall and mobile service fully distributed? Or do they run on compute hosts? What about OpenStack DVR? Do you implement similar technology?
Yes, so basically our load balancing and our security group rules are implemented in a completely distributed manner. So any of those rules or functionality that would be configured by the tenant would be part of the simulation that happens at the compute edge. So yes, it's done in a completely distributed manner. And it sounded like the DVR question was related to the previous. So yeah, DVR brings more distributed L3 decisions, but still there's some centralized functionality like NAT that needs to be done in a centralized place and not in a distributed manner still. So it's still premature in Juno, whereas we've been distributed since day one.
All right. The next question, Cynthia, is do you support network ACK in addition to security group? Are they ACL stateless?
So what it was network? What was it?
Yes.
I didn't catch that. Could you repeat that again?
Oh, okay, sorry. Do you support network ACK in addition to security group? Are they ACLS stateless?
So basically our security groups basically translate to rules and chains, which are lower level, is the lower level underlying functionality. So you can go above and beyond what security groups do in OpenStack by leveraging our rules and chains. So you can basically act on the 5 tuples and do it outside of security group rules, absolutely. So yeah, we have some fine-grained things that you can do there too.
Cool, thanks. Next question, is it possible to modify the routing table of the virtual routers?
Yep, definitely. I mean, so you can add routes and you can add basically like these ACLs to redirect traffic if you like. So they're absolutely tunable that way.
Okay, thank you so much. The last question that we have so far, in case there are no further, can you compare MidoNet with newer New Age and Contrail? What are the key differentiators?
So I can briefly talk about both of them. So basically, some of the similarities with Contrail is they're also open source as well. But of course, they have both of Nuage and Contrail have ties to hardware vendors. So there may be some specific tie-ins to their hardware that they encourage for certain functionality, whereas we're completely agnostic to the underlying hardware.
Okay, thank you so much. Let's see if 1 or 2 more questions pop in. We have a few more minutes left. To those who joined us later, the recorded meetup will be available in the next 24 hours, as well as the slides. And please join our upcoming session, which will be tomorrow, same time, same place, 9 a.m. Pacific to 10 a.m. Pacific. The session's title is going to be latest on OpenStack Trough in the upcoming Kilo release. So let's see. I think that there are no further questions from the audience, but people like this presentation a lot. Just to give you a feedback from one of the participants, this is one of the best and coherent presentations I've ever seen. So thank you very much, Cynthia, for taking time this morning. And thank you, everybody, for joining us. And see you next time. Oh, last question. Oh. Last question. Do you have some figure about the maximum load MidoNet can absorb, like NSX?
Like NSX, is that what you said at the end?
Yeah, some figure about the maximum load MidoNet can absorb.
Okay, so basically, so the compute edge basically handles the traffic flows relevant to VMs on that compute host. So that's why we have the ability to scale out largely. So basically, it kind of is limitless in the sense that compute hosts only handle the traffic that's relevant to them. So I know that's kind of an ambiguous answer, but in the end, it really does scale that way because you're only limited. In the end, it just translates to the number of ports on virtual routers, and in the end, that would be limited by, memory, and still then it would be like it's not something that would be physically feasible to reach that maximum.
All right. Okay, Santa. So thank you very much again, and